right, so this is going to be kind of a standard sort of question. It's also going to be on the final exam at the end of the semester, something similar. So first of all, let's just kind of introduce what we have here. Notice we have a sodium ion. Notice the charge makes it an ion. Here we have a chlorine or chloride ion. Notice the negative charge, that's an ion. Here is iron. Iron is, the symbol is Fe. So we're not going to use I for iron because that's iodine. So we're using Fe, it's ferrous, Greek term. Notice that's an ion also. And now here's an atom. Remember, atoms are electrically neutral, so you wouldn't see a positive or negative. If it is an atom, the protons equal the electrons, okay? Now, these ions here, when they're dissolved in water, and your cells are a watery solution, we're going to call that an aqueous solution. These ions here are essential for important biological functions. So maybe I should restate that. These electrolytes, we studied electrolytes. They are essential for numerous biological functions that are essential for life. For example, sodium ions, not neutral sodium. We saw neutral sodium in a video, and that's a metal, and it reacted and blew up when we added chlorine gas to it, when the guy in the video added chlorine gas to it. So, but the ionic form is totally stable, and it's essential for your brain to function properly. It's essential for your nerves to function properly. Chloride, this ion is also essential for a myriad, a wide variety of biological functions. It's no secret that when a doctor or a nurse does blood work for people in the hospital, they're looking at electrolytes, because when those balance of electrolytes get out of whack or become askew, that indicates problems in metabolism and many other types of problems as well. Here's iron. Now, iron is essential. This electrolyte is essential for the formation of proper red blood cells. If you're not getting enough iron in your diet, your red blood cell counts go down, 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 down. And if that happens significantly, you can move into what's called anemia, which is low red blood cell count. You'd be tired or worse than tired, okay? This is carbon, and this is an isotope of carbon. Another isotope of carbon is this. And another isotope of carbon is this. Notice all these forms of carbon have the same number of protons, the same atomic number. But notice they're differing in their number of neutrons. So that's what isotopes are. They have the same atomic number, same number of protons, but they differ in the number of neutrons. This is a radioactive isotope. So carbon-14, so we can just abbreviate it this way, carbon-14 is used for dating objects. So archaeologists dig up a bowl, let's say it comes from civilization, they're not sure how old the civilization is, but they can do an analysis of carbon-14 and then plug it into a pretty simple mathematical formula and come up with the age of the object. So maybe the bowl was made in 1,500 years ago. And by the way, that's pretty accurate. It's a plus or minus maybe 150 or 200 years in terms of the accuracy, which is pretty good considering that bowl was first made over 1,000 years ago. Well, what I want you to do now, quickly, for each of these, let's write the number of protons, neutrons, and electrons for each of these. So go ahead and do that. Another kind of easy kind of softball question. Hit softballs, Nick, hit them right out of the park. I could say pick the atom out of the four. Nick, what do you think? Which is the atom?
What do you mean?
Which represents an atom as opposed to an ion?
Oh, the last one.
Yeah, that's an atom because there's no charge on it. So these are ions, right? And of course, if they're dissolved in water, they're electrolytes, and these are important electrolytes for biological activity. Nerve, brain, heart function. Let me say it again. Electrolytes essential for nerve, brain, heart function. The proper balance, okay? Well, this one's pretty easy. Nick, this is kind of fun because I can call on you a lot. How many protons in, we're going to do this now, everybody. Let's start with carbon-14, this isotope. How many, Nick's going to answer this for us. How many protons here?
6.
6. How many neutrons?
6.
Do the math, Nick. Subtract.
8.
Yeah. This is going to be, these are found in the nucleus, of course. So that dense central core of the atom is going to house, basically the mass of the atom is in that tiny core, and it is tiny. Interesting to note that a typical atom, the nucleus of a typical atom, is 1/10,000th of the total volume of the atom. That's amazing, meaning the atom, a single atom, is mainly space, because the hard stuff, the nucleus and the protons, are in a tiny, tiny, tiny dot, so to speak, in the center. And it's 10,000 times smaller than the rest of the atom. It's amazing. Anyway, Nick, if it's an atom, protons equal electrons. So tell me what I put here for electrons.
6.
Okay, easy enough. Somebody at home, give me the number of protons. We'll do the easy ones first. Somebody at home, give me protons, protons, and protons. Let's see, Allison, how many protons in sodium?
12.
Can you see that number there or not, Allison?
Kind of.
It's 11?
Now 11.
Okay. What about this, Ava? That's 17. That's the atomic number. That's an important term. Number of protons. Ava, how many protons in this ion?
17.
Easy, easy, easy. What about for iron here? Somebody else at home. That number, the lowest, that number that's down here low is 26. What is it? Somebody at home?
24. 26.
Wow. Oh, I get it, though. You're jumping ahead, Mr. Bauer. Actually, now it's making perfect sense, and I like it. So this is 26. Number of neutrons. Easy here. Just subtract the lower number, the atomic number, from the mass number. So let's write 18. 18 for Cl minus. If you're having trouble seeing that, write it. And by the way, I'm videotaping this, and I'll put it on YouTube. And it'll be clear because I'm using my phone and not this camera, which isn't that good. Let's see. Can anybody tell me neutrons for sodium?
12.
Yep, you got it. Now let's talk about electrons. And oh, we need to do neutrons for iron here. Somebody at home?
30.
Okay, easy. Please don't miss anything here. For so far, don't miss anything. Don't miss a thing. So simple. Now, though, it gets a little trickier. Notice atoms have equal number of protons and electrons, so that was easy. But let's take a look at Na positive. What happened with sodium? Sodium gave an electron away, and now it has a positive charge. Why does it have a positive charge? It gave an electron away, and now listen to this. It has one less electron compared to protons. So we've got 11 positives here. So we're going to have 10 negatives. Notice 10 negatives, 11 positives. If you do the math, remembering that protons are positive and electrons are negative, 11 plus, if you did this, 11 plus negative 10, it's going to equal positive 1, and notice that's where that positive comes from. If you lost 2 electrons, you would be double positive. If you lost 3 electrons, you'd have a triple positive charge. Somebody at home, now we got a different situation. The chlorine gained an extra electron. So somebody at home, how many electrons does Cl have? Cl minus have?
I said 18. 18.
Thank you. So that is correct. Let's do the math and check. Excuse me if I'm insulting your intelligence here. Excuse me. But I just want to make sure everybody's on the same page. So notice you have 17 plus a negative 18. That equals negative 1, and there's negative 1. Obviously, if we gain 2 extra electrons, then you'd have 2 more electrons compared to protons. Okay, Bradley, you're good at this. So how many electrons in my iron double positive ion?
24.
There you go. All right, good.
Nice job, Bradley.
Thank you. And no chatting, please. No offense, but we got a bunch to do. Thank you. Let's see here. Let's take a look at the carbon atom. Here's another example of maybe a 6-point question. Rewrite this where you got some room now underneath, so you don't want any of this stuff in the way. I'm going to erase all this. So go ahead and draw a picture of the carbon atom showing the number of protons, neutrons, and electrons, and where those structures are. Where are the protons, neutrons, and electrons for this? It is an isotope, remember, for this isotope of carbon. Go ahead and do that. So I've done this in one of the classes. In the other class, I chose a different element to form a compound. Protons, neutrons, and electrons. 6, 8. You with me on this, Nick? With me with 8? Okay. There we go. And let's go ahead and draw 6. I'm going to make this fairly big here. 6 positives, 8 neutrons. Energy level 1, energy level 2. Notice I don't need an energy level 3 because I only have, let's make sure that looks like a 6. Notice I don't need a 3rd energy level. It's simply not big enough. There's not enough electrons to enter a 3rd energy level. Here's what you need to have. You need to show 2 electrons in the 1st energy level, and then you need to show 1, 2, 3, and 4 electrons in that next energy level. Important question here. How many valence electrons are present?
4.
It's 4. Thank you. Next. On the test, I'm not going to give you the same one. You just have to use the principles that we're using here. Okay? Well, let's see here. Oh, gallium-67. Yeah, that's another important one too. And so you put gallium. What we're doing for people at home, I restarted this video. These are radioactive isotopes that are used in science and medicine. So carbon-14 is going to be used to date materials, date artifacts from archaeological digs, for example. So that's not biology, but it's interesting and important. This is cobalt-60. Cobalt-60 is radioactive, and it'll be used to shoot high-energy radiation at cancerous tumors. Iodine-131, good review for the people, we just talked about this. Iodine-131 will be taken in by the thyroid gland, which is in this neck region, and it can be used to assess thyroid function or maybe possibly treat thyroid cancer. What was the gallium one again?
Gallium-67.
Gallium-67, and what do you have for a medical use of gallium-67?
It detects and monitors certain types of cancers.
Yeah, detects and monitors certain types of cancer. So there's a wide variety of uses for radioactive isotopes. Again, these would be important questions to know, memorize here, the answers for the test. Let's talk strong, weak, and non-electrolytes. So I'm going to throw out some and you come back with the answer, strong, weak, or non-electrolytes. So now it's time to just talk out. What do you think? Anybody? If I take table sugar and if I stir that in water and do an electrolyte test, is it strong, weak, or non? Anybody? Non. It's interesting that table salt dissolves, or I'm sorry, that didn't come out right. It's interesting that table sugar dissolves, as we know from Kool-Aid and soda, but it does not, and this is key to remember, it does not ionize. So it dissolves, but it doesn't separate into ions. On the other hand, what about table salt, sodium chloride? What about that? Anybody?
Strong.
Yeah, notice. NaCl solid. If you put that into water, it will break apart and separate into, yes, separate ions. And by the way, isn't that easy to remember that sodium chloride is joined with an ionic bond? Because isn't it easy to remember that sodium chloride ionizes? Listen to that word, ionizes in water. So that has to be an ionic bond, as opposed to a covalent bond, which is like for CH4 or H2O or many, many, many other things. What about this? Tap water, did our tester for tap water show electrolyte activity?
No.
It did not. In reality, if we had a more sensitive test, tap water is a weak electrolyte, but you don't have to write that. Our test didn't show it, but our test is not very sensitive. What about this? What if how about if I take a weak acid? We talked about acids and bases today. Acids and bases. A weak acid, what can we say about electrolyte activity for weak acids? It's a weak electrolyte. That was easy. What about strong acids? Strong acids. Strong electrolyte. How about this? We talked bases today. A strong base is a strong electrolyte. A weak base is a weak electrolyte. Well, speaking of acids and bases, acids release a certain ion into water. What do acids release into water? What do acids release? What do acids release into water? Nick, study what we did today. Somebody at home.
Hydrogen ion.
Hydrogen ions. Acids release hydrogen ions. Notice, let's get rid of that. Notice if we had HCl in kind of a gas form, so a G for gas, but if we bubble that into water, it ionizes like that. That kind of reminds me of NaCl. You put it into water, it ionizes in Na positive and Cl minus. Notice that's an acid. By the way, what do acids do to the pH of neutral water? If I measured the pH after I added this acid, would the pH go up, down, or stay the same? Anybody at home?
Down.
Down. The lower the pH go, the stronger the acid. What is, just as an example, in one of the classes today, the fifth period class, we tested the pH of vinegar, and it was about 2.6. Remember the scale, just to remind people in case you forgot or weren't listening today in class, the scale goes from 0 to 14, 7's neutral. So vinegar, which is a weak acid, is about 2.6. What do bases release? Well, let's get rid of that. So there's our acid releasing H positive. What do bases release? Somebody at home.
Hydroxide.
NaOH, sodium hydroxide. Notice I have this in blue because bases turn certain dyes blue in color. Acids turn certain dyes red in color, that's why I chose red. But notice, Na positive is released, OH minus is released, that's hydroxide. That's a strong base. The pH of this solution goes up, the pH of this solution goes down. Really, really, really important. How about this? Homeostasis, the ability of living organisms to maintain a steady state or a steady internal environment. That's one of the 8 characteristics of life. Know the 8 characteristics of life. Got 2 cameras here. Know the 8 characteristics of life. Know them. Remember that for something to be considered living, it has to have all the characteristics. 7 out of 8 doesn't cut it. The coronavirus is not living because the coronavirus is not made up of a cell. A virus is not a cell. The coronavirus cannot reproduce unless it enters a living cell, and that's why it makes us sick, because it infects living cells and causes them to die eventually, and then it can reproduce. Getting back to homeostasis, blood sugar, so blood sugar here is going to be maintained within a range here. So it might be approximately 110 value, a little bit high, a little bit low. And it's decigrams per deciliter, I believe. Let's say after a meal, blood sugar goes up. So here's blood sugar rising. What does the pancreas, somebody at home, what does the pancreas, it has cells that detect the rise, that's kind of cool in and of itself, but what does the pancreas release? Yeah.
Insulin.
Yeah, so, and by the way, insulin is an important hormone, and when insulin's released, blood sugar goes back down closer to its steady state range here, somewhere around 110 value. Okay? So important. If blood sugar stays high, that's a problem. Houston, we've got a problem. If it stays high for sustained periods of time, it can result in blindness, for example, or maybe amputation of the limbs because it's going to mess with all sorts of the body's physiological processes. That's high blood sugar over a long period of time. Okay, how about this? We start going down because we haven't eaten in a while. Have no fear, Nick, have no fear. The pancreas is here. The pancreas detects that. So, pancreas, the pancreas releases a hormone called glucagon. And glucagon, the ultimate effect of glucagon is going to be to raise blood sugar and get it closer to that steady state range. Now, a great question would be, how does that happen? Somebody asked it in, I believe it was maybe 8th period. How does that happen? Glucagon stimulates the liver, organ located right here, and the liver stores excess amounts of sugar in kind of a special storage form, and glucagon activates the liver into releasing that special sugar form storage molecule into the blood, and we rise and we get closer to that homeostatic range. Why is all this happening? Because the brain cells are very sensitive to sugar amounts. So the body's working hard to keep sugar in a steady state range to keep the brain cells happy. They're taking priority. And I don't think I mentioned that in either class, but that's the reason there's all this time and effort for blood sugar steady state or blood sugar homeostasis. Here's a big one. You can do this on your own though because it's straight out of the notes. I mean, this is a big question in terms of point value. Nick, no yawning in here. 0 yawning. Okay? Okay, let's go. Oh, by the way, for people at home, how far away is Nick? How far away are you from me?
Like 15.
No, it's more than 15.
Like 20.
More than 20.
Really?
It's about 30 feet away, so that's why I don't have a mask on. Anyway, here's an important point value, but again, it's straight out of the notes, so I'm not going to go through it, but I'm alerting you to the fact. List 5 unique and important properties of water and explain each. So, for example, you'd say water has a high specific heat capacity, but you got to explain it. You get 1 point for saying high specific heat capacity, but what that means is water can gain heat, lots of heat, and the temperature change isn't going to be that much relative to other substances. Conversely, water will release heat, but the temperature of the water doesn't drop that much. My explanation for that, which I gave to one class but not the other, think about this. If you put a metal, like aluminum metal, let's say, on a hot plate, and if you put a beaker full of water, and the beaker and the metal have the same masses, the metal, let's say they're both 50 grams, and you have equal amounts of heat, if you touch the metal, and if you put your finger in the water, within a very short time, ouch, touching the metal would cause your finger to feel that increase in temperature because the metal's temperature is rising quickly. But now, here I am in the water, and it doesn't feel like it's very hot yet. It'll eventually get there, but the metal absorbs heat really quick with a big temperature change. The water, it absorbs the same amount of heat with a small temperature change. So maybe that helps. Some of the other aspects of the unique properties of water are easier to understand and explain. I'll leave you with this. Water is polar. Part of the water molecule has a partial negative charge. The other part of the molecule has a partial positive charge, so maybe this will help you in terms of understanding. Here's my other polar molecule, a negative side and a positive side. Notice here